Welcome to 3 Lanes number 49. We made it to 49. Just housekeeping items before we start. But remember to listen to the podcast at 1.3 speed at least. I always listen to stuff at 1.5. I know I can speak slow, so please listen to it a little faster. I mean, I can always speed it up while editing, but I try not to edit as much for this specific podcast. I just like put it out just because it's something that I feel like it's not talked about a lot, or the subject that I'm covering, it's not something that has been talked about a lot, or it's something that I would like to listen to, or something that I would have kind of like in my back pocket and listen to it later. But today we'll be talking about technologies that the watch industry has developed and that have been adopted by other industries and vice versa. So I would like to again keep it to like 15 to 16 minutes per episode, not too long. I feel like that's the sweet spot. If you are listening to somebody talking by themselves, I don't want to spend an hour or 30 minutes talking, mainly because you can, I don't know, I feel like sometimes podcasts on their own can be monotonous depending on the people that's or the person that's talking. And I don't want to fall into that. I know some episodes might have been like that, mainly because I'm learning how to do this on my own. So without rambling any further, let's begin. The first technology developed from the watch industry is Swiss machining and precision manufacturing. This is one of the biggest ones, and as a manufacturing engineer or hardware engineer, I've seen this a lot. So it's basically not because stuff is made in Switzerland, but it's because how the process is made. So it's Swiss machining that it was developed in the 19th century by a Swiss watchmaker Jacob Schweizer, and he developed this to produce precision components for obviously wristwatches and pocket watches. But it was originally created to manufacture the intricate miniature parts that are required to manufacture watches. And the manufacturing technique became indispensable across multiple industries. And today, Swiss machining is extensively used in medical device manufacturing, and particularly for producing surgical instruments. Let's see, like catheters, dental equipment, microneedles. But the technology allows the production of components with very, very tight tolerances. Again, this is used in the medical industry. Also, the aerospace industry uses it a lot. Automotive industries, they rely heavily on the Swiss machining. And because they produce a lot of complex, high precision components, again, the tolerances are pretty tight. So that this technique allows manufacturing to create small pieces very accurately, and it is ideal for applications requiring both strength and precision in compact form factors. Then the next technology that we have is quartz crystal technology. So this one was developed by Seiko in 1969 with the Astron quartz wristwatch. And again, we've spoken about this before, and it transformed horology. You can say for the better, for the worse. It kind of almost killed it, but we still have watches, luckily, among us. So and quartz was developed, and like Grand Seiko, like we spoke about a couple episodes ago, they developed their the spring drive. I don't know why I blanked on that, but their spring drive technology, which uses quartz and mechanical components as well. But this technology expanded more than just into watches, and it's basically everywhere now in modern electronics. Today we have quartz oscillators, which are essential components in computers, smartphones, home appliances, cars, industrial equipment, anything, right? So there's one specific CMOS integrated circuits developed by Seiko for ultra low power watches in 1971. And this basically consume 1/3 to 1/4 of the power used by ordinary integrated circuits or ICs of that era. I think we spoke about the CMOS maybe or the development of the AE1 program, if I remember correctly. But again, this is expanded and it's used in consumer electronics, computers, cell phones, anything that you can think of. You might have a quartz oscillator in it. Next one, LCD display technology, or LCD, or just LCD. This is the liquid crystal display technology, and its pioneer for watches became it was pioneered by for watches. Sorry, it became foundational for modern consumer electronics. And in 1973, Seiko Epson released the world's first 6-digit LCD digital wristwatch. So the Seiko Quartz LC VFA 06LC. And it had an LCD technology. It offers superior readability and power efficiency compared to LED displays. So it's not the same, right? LCD is not the same as LED. The LCD technology developed for watches evolved into twisted pneumatic TN liquid crystal displays, and it became widely adopted by electronics manufacturers as a core technology for displays in TVs, smartphones, computers, projectors, and smart glass. So everything that we use now, right, it uses LCD. But before being incorporated into all these products, Epson used LCDs in TV watches in 1982, mobile phones in 1993, and pocket-sized color TVs in 1984. That's crazy. But the National Museum of Nature and Science in Japan recognized this technology as one of the essential historical materials for science and technology in 2019. Next technology developed by the watch world, used in the everyday world now, is the miniaturization of technology. So obviously watches are smaller. They use gears that are smaller. Everything in a watch is smaller. So this influenced the medical device development. So the precision required to create mechanical watch movements with hundreds of tiny components translate into capabilities for manufacturing miniaturized medical devices such as pacemakers, continuous glucose monitors, and sensors that you can implant inside patients, right? So the Medtronic Micra, the world's smallest pacemaker, is a perfect example of how miniaturization techniques have pioneered in watch, or techniques that the pioneer in watchmaking enabled revolutionary medical innovations. So these miniature devices improve the patient comfort and reduce invasiveness of big devices and enable continuous health monitoring that would have been impossible with anything bigger. And you're probably seeing a picture of it now on the screen if you're watching the video. If not, then think of it like as a size of a tiny pill. That's the size of the peacemaker, which is crazy to me. Next technology is micro machine components and jewel bearings. As we know, or if you didn't know, now you know, gears need what do you call it, lubrication to move, right? So if you don't have a lubrication, then the friction is too high and then things break. But in this sense, jewels are used in watches to keep everything lubricated and to reduce friction. So this usage of synthetic rubies and sapphires, that it's usually used as bearings in traditional watch movements, and it's because they're really hard. They have a lot of wear resistance and low friction coefficient. Now they have found the application in medical implants and surgical instruments. Companies like Pierre Gasser apply their watchmaking expertise to manufacture precision jewel components for cardiovascular, neurosurgery, and other very invasive medical applications. They achieve very high accuracies of for a whole diameter, you could say. Now we're gonna switch it up, and we're gonna talk about technologies from other industries adopted by watchmaking. By the way, this podcast was inspired by a previous podcast from Collective Horology, which I listened to it very, very religiously every Sunday/Monday that they release it. But yeah, sometimes I get really, really good ideas from them, Asher and Gabe. They're not just good with good watch brands to discover and to promote, but and obviously sell. But they also have really, really good topics in that podcast. If you haven't listened to it, this is the shout out in the middle of my podcast to them. But yeah, so the first technology from other industries is the advanced materials from aerospace and automotive. So what am I talking about? I am talking about materials developed for aerospace and automotive applications like carbon fiber, ceramic matrix composites, and advanced titanium alloys originally designed for aircraft and spacecraft have become very, very prominent in luxury watchmaking. So the German Aerospace Center, DLR, collaborated with IWC to develop watch cases from carbon fiber, and these were reinforced with ceramics, materials originally used in spacecraft, thermal protection shields, and satellite propulsion systems. But these materials offer really exceptional hardness, scratch resistance, temperature shock resistance, and lightweight. These properties are very, very critical for both aerospace applications, and you could also say, you can make the case for luxury watches. So, carbon fiber has been used extensively in aviation, aerospace, defense, automotive sectors. It has been incorporated into watch cases since maybe 1990s. Brands like Panerai develop proprietary materials such as Carbotech, and Ulysse Nardin introduced carbonium, an upcycle aerospace grade carbon material composed of 95% carbon byproducts from the aeronautical industry. And these materials provide exceptional strength to weight ratios and distinctive, very, very distinctive aesthetics. On the other hand, we have ceramic materials, particularly zirconium oxide, titanium, and special alloys like IWC ceratanium, which where they combine the titanium and ceramic properties. They have crossed from aerospace and industrial applications into watchmaking. These materials are nearly 4 times harder than stainless steel and almost scratch proof. Highly resistant to corrosion, but ceramic materials are pretty brittle, so if you throw it to the floor, you might shatter it. So don't do that. Next application would be silicon and anti-magnetic technology. So modern technologies or modern electronics and semiconductor technology have revolutionized watch movements through silicon components. So silicon is famous for being non-ferrous and naturally resistant to magnetic fields. So it's not, you could say, it's not a metallic material. So that's why it's not magnetic. And it has become the ultimate anti-magnetic material for watch escapements. Again, Ulysse Nardin presented the freak concept, which you might be looking at a picture right now. This watch with a silicon escapement wheel in 2001, an innovation subsequently adopted by many, many brands. But the freak, it's not just it's not different because of the silicon escapement, but also the shape and how it everything aesthetically about it was different. Next, the silicon components offer multiple advantages. They're lighter than metal, less prone to deformation from gravity, they're resistant to magnetic fields, and have superior corrosion resistance. With this technology now implemented, now we're addressing something that's actually really, really increasing as more electronics become the norm. And this is the proliferation of magnetic fields from anything electronic, right? Smartphones have it, laptops have it, medical equipment, other electronics that can disrupt mechanical watch accuracy. Anti-magnetic watches using silicone and other non-magnetic materials can withstand magnetic fields up to 15,000 Gauss and this exceeds the ISO 764 standard of 60 Gauss. But next technology, sorry, is smartwatch technologies and sensors. Again, this applies only to smartwatches, but again, watches nonetheless. But it's basically the joint or convergence of traditional watchmaking. If you don't know if this sound that I'm making, it's my hands coming together. So that's the convergence sound. The convergence of traditional watchmaking with I don't know about traditional, but the convergence of the usage of a watch with consumer electronics has introduced a lot of sensor technologies originally developed for medical devices and smartphones. But modern smartwatches add uh, the sensors for heart rate monitoring, for blood oxygen measurement, accelerometers, any sensor that you can imagine. You might have it on a smartwatch. But this technology, it was originally developed for standalone medical monitoring devices, and it has been miniaturized and integrated into wrist worn formats, just like the Apple Watch or like the Phoenix Garmin Phoenix. But it has different functionality, like checking your blood pressure, uh, your steps, your movement, all that stuff, right? So it's decades of medical sensor development, and it's now accessible in consumer wearables, which is pretty cool if you ask me. I don't have one, but I think still cool. I'm glad the technology exists. But all this can now integrate with smartwatches, and it allows, for example, diabetic patients to monitor blood sugar levels in real time on their wrists, which I think is pretty useful. Next technology developed that it was adopted by watches is wireless communication. Again, this applies for smartwatches, but the near field communication technology is something widely adopted in smartphones, payment systems, and it has become integral to smartwatches. And I don't know if there's any hybrid timepieces. I would have to look into that. But NFC enables contactless payments, device pairing, data exchange, functions that have expanded the basically the utility of devices in general beyond just, for example, a smartwatch just being a timekeeper. No, you can use it for many other things. So the NFC smartwatch market, it's valued at 25 billion. It was valued 25 billion in 2024, so not even 2025, 2024, and it's projected to reach 50 billion by 2033. 33, with over 80% of survey consumers using smartphone or smartwatches for contactless payments. This technology transfer has transformed watches into basically a wallet, payment devices, and you can access credentials and connectivity hubs on them. Next one, we have solar and kinetic energy harvesting. This one doesn't just apply. I don't think smartwatches do solar or kinetic energy for that matter. But solar cell technology developed for renewable energy applications has been successfully miniaturized for watches. For example, Citizen launched the world's first analog solar power watch in 1976, and it was followed by Seiko in 1977. The modern solar watches like Seiko's GPS Solar Astron or the G-Shocks, which I really love, the G-Shock squares that are solar. I only have one, but I should have more. Don't tell my wife I said that. But this demonstrates how photovoltaic technology can power even complex GPS-equipped timepieces. Seiko's kinetic technology, original called Auto Quartz, launched in 1988, and it adapts principles from renewable energy generation to wristwatches. And an oscillating weight captures the kinetic energy from the wearer's movements, which a generator converts to electrical energy, and it stores in a lithium ion capacitor. This then self-sustains the watch, and it eliminates battery replacement and reduces environmental impact. A renewable energy concept applied at the micro scale of something like watches. Finally, we have waterproofing and nanotechnology. So here we have advanced waterproofing technologies developed for consumer electronics and have been adapted for watches. I think we can call it mainly for smartwatches. I don't think regular watches use this type of coating, but nanotechnology based coatings using chemical vapor deposition, they create ultra thin electrically insulating barriers, and this protects the electronic components from water damage. So there's companies like HZO and P2I. These companies develop nano coatings for smartphones, tablets, wearables that create hydrophobic and oleophobic barriers at molecular levels. These coatings, applied to printed circuit boards and internal components, enable devices to achieve IPX7 or IPX8 waterproof ratings without any having any actual seals or gaskets on them. So smartwatches and hybrid watches have adopted these technologies to achieve waterproofing while maintaining sleek profiles. Again, I don't think this is used on regular watches because obviously we don't have printed circuit boards in regular watches. So it's not something that is going to protect any water to coming into the watch. No, it protects whatever's inside the smartwatch. It's already coated on it and it's not going to get damaged. That is basically it. So that's what I have for today. I'm not doing a 4P analysis today, which is price, place, promotion, um, and product, because it doesn't apply here. We're just talking about technologies developed by the watch world or developed by other industries and applying to the watch world. I hope this has been interesting to you. I'm already 22 minutes. This is amazing. I'm already over, but thanks so much for your time. I will see you next time.